All right, before we start into the ideal gas law, there's a couple of relationships which are laws in and of themselves, but we want to talk about these first. The first one is the law of combining volumes. This one is related to the way gases react. So if you carry out a chemical reaction with gases, then the volumes of the gaseous reactants and products measured under the same conditions of pressure, temperature, are always whole number ratios. Okay, and this arises again out of the coefficients of the reactants and products in the chemical reaction equation. Avogadro's law talks about equal volumes of gases containing the same number of particles regardless of their mass. And so what this kind of means to us, there's two things. We kind of bring out the molar volume of a gas. That is, if we have 1 mole of a gas, let's say under STP conditions, then that volume is always 22.4 liters. Under SATP conditions, then it's going to be 24.8 liters. And so we call this the molar volume. So 22.4 liters per mole of any gas and 24.8 liters per mole of any gas. Those are important numbers to know, and we can derive them from the ideal gas law, which we will present in the next slide. But these numbers are good to know for a number of the questions that you're going to be working on for homework. All right. The ideal gas law is simply that an ideal gas conforms to the assumptions of the kinetic molecular theory and follows the gas laws exactly. Now, in reality, there really is no such gas. However, what we find is that most gases behave as ideal gases, or at least to a fairly strong extent, if high pressures and low temperatures are avoided. All right, so let's derive this ideal gas law. Let's start with our combined gas law. So P1 V1 over T1 equals P2 V2 over T2. And let's use our molar volume. So let's take, in this case I've taken STP conditions. So 101.3 kilopascals, 1 atmosphere. 22.4 liters per mole. We got that from our molar volumes. And 0 degrees Celsius, so that's 273.15 Kelvin. So now if we, and that's for 1 mole of a gas. So if we replace the 1 mole with any number of moles, say n moles, then we end up with this formula. And really, this is exactly it, just a formula. Now, this part here with the numbers, because these are always STP conditions, and because it's a per mole volume, we can essentially get a constant value out of that. And so we'll call this constant, let's say R. All right, so we rearrange all those symbols and put the variables on one side and the numbers on the other side, and we get PV over NT is equal to all of this mess, which we're going to call our universal gas constant, R. Okay. Now, rearranging it, it's usually written down as PV equals nRT. And that's the ideal gas law. My old professors used to help us remember, they used to call it the pervert equation, but you can call it whatever you want. Pervert, I don't know. Anyway, you got to remember it somehow. PV equals nRT, that's the ideal gas law. There it is. All right, so what does this look like in terms of an example? Oh, a couple of things. The R value. Depending on the units that you use, and most of the time we'll use either kilopascals or atmospheres. the value is 8.314 for if you're using kilopascals as your unit for pressure, and 0.08206 if you're using atmospheres for your unit of pressure. All right, let's do this example. 2.5 liter container is filled with sulfur dioxide at a pressure of 120 kilopascals and a temperature of 27 degrees Celsius. Calculate the mass of sulfur dioxide gas in the container. All right, so we're again, pick out the information. So volume is equal to 2.5 liters, temperature 27 degrees Celsius. Of course, we need to convert that to Kelvin, so that's 300 Kelvin, and the pressure is 120 kilopascals. So we're going to do two things here. First, we're going to calculate the number of moles of the gas, and then we're going to switch to calculating the mass from the number of moles, which we've done a million times already. So here we go. N is equal to PV over RT. So our ideal gas law, just solving for N. Plug in the numbers, and we get 0.1202 and a bunch of decimal places moles. And then using the molar mass for the gas, sulfur dioxide, SO2, which is 64.06, multiply that by the number of moles, and we get 7.7 grams, 7.71 grams. 3 sig digs from the question. And there's your final answer. All right, so here's the homework. Again, try these and bring questions to class.